Okay, so we're going to start out today by looking at section 2.5, which is on solving inequalities. But we're going to look at inequalities that aren't just linear. Now they're going to be up to quadratic, okay, or even cubic. So inequalities where the highest exponent is a 2 or a 3. So we're going to start with a formula we've had before. And I know this isn't an inequality, but I can easily make it one by changing the equal sign to a less than or greater than. Okay, so we're going to do something with this as an inequality. So this is the formula for projectile motion. I don't remember what section, but if you want to copy it down again, you can. So it tells you how high an object is based on a few different factors. How long has it been in the air for after you've thrown it? How hard was it thrown initially? That's your initial velocity. And what was the initial height of the object? Okay. Did you throw it off the top of a building? If so, it's already a certain amount of feet off the ground. If you have a problem that says it's something's being thrown from ground level, the initial height is 0. Okay, so let's see if we can set up an inequality in a second based on what they're telling me right here. So it says a ball is thrown straight up. It doesn't really matter if it's thrown straight up or it's thrown at an angle. That makes no difference at all. Okay, but a ball is thrown straight up from the ground with an initial velocity of 80 feet per second. I want to find, well, you know what, actually, before we even do that, let's just figure out what the formula would be to model that. So a ball is thrown straight up from ground level with a speed of 80 feet per second. So the height of the object, the negative 16, that never changes. So negative 16 t squared plus initial velocity. Isabel, what's my initial velocity here?
80%.
How much?
80 feet per second.
Yeah, exactly. So you're going to plug in 80 feet per second for v sub 0 plus my initial height. Isaac, what's my initial height?
0.
0, right? It says ground level. So that's a formula that tells me my height of my object under these conditions. Now, they want to know when the ball is at least 64 feet above the ground. Okay, so this, what's in that box, that's the height of the ball. Height of ball. Now, if you want to know when something is at least 64 feet above the ground, what does that mean? At least 64 feet. Jake?
64 feet or higher.
64 feet or higher. So the question is, when is the ball, the height of the ball, greater than or equal to 64 feet? That's what we want to know. So we're going to fill in our formula for the height of the ball, right there, and then solve it, and they want us to do it on the graphing calculator. So we've got negative 16 t squared plus 80t. That's the height. And when is it greater than or equal to 64? Now, when we solve even like a quadratic equation, what number do we usually get on one side? Yep. Yeah, let's do the same thing here. So negative 16t squared plus 80t minus 64. Okay, so now what I'm going to do is graph that and see what it looks like on the screen. If you got anything else in there, just get rid of it. Remember, for the variable, make sure you use x. You can't use anything besides x. Plus 80x minus 64. Now, I got to set my window. Well, x is time. So does negative time make sense here? Think, Rebecca? Maximum time, well, that's how long it's in the air for. We don't know that yet. So let's put 10. And if the ball goes off the screen, then we'll fix it. Okay. Y is our height. Greta, negative height, does that make sense?
No.
No. The lowest the height can go is 0. What's the highest it can go? That I don't know. Let's just try 100 feet. And if the parabola goes off the top of the screen, we got to go higher. All right. So there's our parabola. So what we want to know is basically when that parabola is greater than or equal to 0. Well, that's the section I'm showing you right there. It doesn't make sense to look at negatives, but for a second, I'll just show you the negative part. Parabola definitely goes negative at some point. But all we're concerned with is this section right there. That's the part that is above or equal to 0. So how would I find this point and that point? What would I have to do? Oh, Emma?
0.
Yeah, we're going to calculate a 0. So second calc 0. Okay, I'll do the one on the right. If someone else can do the one on the left, that'll help me out. So pick a point on the left, pick a point on the right, do a guess, and we get 4 seconds. So at 4 seconds, the object is exactly back at 64 feet. And that's on the way down. Now, on the way up, what time does the object finally get above 64 feet? What time does that happen at? Emily? 1 second, okay. So between 1 and 4 seconds, this object will be above 64 feet. If you didn't want to solve it this way, another way you could have done it, I see some people do it, they leave the 64 right where it is. They leave the negative 16t squared plus 80t, they leave that alone on the other side. And they graph what's on the left and what's on the right in 2 separate equations. A line is going to come in at 64. And now you're interested in this part right here. That's when the ball is above 64. We moved the 64 to the other side, so we were looking when it was above 0. But if you do second calc intersect, blue, red, do the guess. I won't do the other one, but you get exactly the same answer that I got the first time. 4 seconds. Okay. So on the way back down, it hits 64, and on the way up, it hits it at 1 second. It's anytime between 1 and 4 seconds. So now, let's see if we can figure out how long the ball was in the air for. Okay. What does that mean about the height? If the ball is still in the air, that means what? What?
It's greater than 0.
Right. So now we're looking at the height of the ball. It has to be above 0. Okay, so let's go back and get my formula. The height of the ball is negative 16t squared plus 80t. When is that greater than or equal to 0? So don't put 64 this time. They don't want to know when it's above 64. They want to know when it's in the air, which means it's above 0. All right. So the way we're going to have to solve that is if we look at the left-hand side, Does anybody see a number that we could factor out of the negative 16 and the 80? A number that goes into both. Shot?
8.
8, yep, even bigger. Yep. 16, yeah, we can factor out a 16. In fact, I'm going to factor out a negative 16. Doesn't really matter, but you'll see why in a second. Anything else that they both have in common besides negative 16? Yep.
T.
A t. So let's do that too. If I do that, I'm left with t right there. We can check it. Negative 16t times t. It's negative 16t squared minus. And what else would you be left with? Negative 16t times what is 80t?
Five.
Yep, 5. Now, look at what we've got right there. We've got something times something is greater than or equal to 0. Something times something is greater than or equal to 0. How can you multiply two numbers together and get something greater than 0? Actually, it technically wouldn't be equal, because if it equaled 0, then the ball would be back on the ground. So technically it has to be just above 0. Okay. But yeah, same question. So how can you multiply two numbers together and have them come out greater than 0? Yeah, Mike.
Either of them can be negative or 0. Or
So you could have a,
you could have double negative.
sure, negative times negative would definitely come out greater than 0. Anything else?
Positive, positive.
Positive, positive. Okay, we've kind of done this reasoning before. Only one of these makes sense here. Think about t. T is time. So t is guaranteed to be what kind of number?
Positive.
T is always a positive number. Well, if this is always a positive number, because it's time, and you take a positive number times negative 16, what does that mean this is always going to be? Yeah, that's always going to be a negative, no matter what you do. Time is always positive. So a positive times a negative means that part is always negative, which means that's the situation we're looking at. The only way that that could ever come out greater than 0 is if this was also negative. You have no choice over the first one. It's always negative. So the second one also has to be negative. And then a negative times a negative is always greater than 0. So now we just have to answer the question, when does this happen? When is t minus 5 negative? If we can figure out when t minus 5 comes out negative, then we'll know exactly how long this ball is in the air for. Right, so when is t minus 5 negative? When t is less than 5. So how long is the ball in the air for? Less than 5 seconds. What does that mean exactly? Well, it means it's like 4.9 repeating. So it's in the air just under 5 seconds. Okay, any question on that? Now, that's not too bad because all you had here was a squared and then a number with t. If you had something like that's fine to do. That's still okay. But then when you add another number at the end, and now you want to know when that's greater than 0, this is going to mess me up. All right. If that wasn't there, I could do exactly the same thing I just did before. Factor out an x, and then do it like that. But you can't factor an x out of the 6. So I've got to show you a way to solve it when there's a number there. And that's what we'll look at next. Yeah. Okay, and the way you solve it when there's a number there is we're going to make what's called a sign pattern. What a sign pattern tells you is basically whether the result of a calculation is going to be positive or the result of a calculation is going to be negative. That's what it tells you. And I'll show you how we make it. Alright, so the whole key to doing a sign pattern is being able to factor. If you can't factor it, you can't use this method. So if I ask you to do a sign pattern, I will definitely give you a problem that's factorable. So what do I mean by linear factors? Okay, a linear factor, usually you see these in parentheses when you're factoring, is anything where you have a letter plus or minus a number. There's no exponent on the letter. Okay, that makes it linear. X plus 7, 3x minus 8, 2x plus 6. Those are all linear factors. If you take and throw an exponent on one of the letters like that, that's not linear anymore. Okay, it has to just be a letter plus or minus a number. And you can have a number in front of the letter too. Like there's a letter in front of T, right? It's just a 1, we just don't write it. And the idea is that every factor I wrote on the board has exactly one number you can plug in and make it 0. I could plug -7 into what I just circled and it would be 0. I could plug 1 in right there and it would be 0. I could plug in -4 for T and it would be 0. Okay. There's no other number. There's only one number that makes it 0. Any question on that? So what that means is if you can find out the one number that you plug in that makes it 0, then you know anything bigger than that number, when you plug it in, you'll get a positive result. Anything less than that number, if you plug it in, you'll get a negative result. So we have to just find where it's 0, and then we know bigger would be positive, smaller would be negative. Okay, we'll do an example. And the way we're going to show where it's positive and where it's negative, we're just going to make a picture. We'll draw a number line. I'll do a number line for the bottom one. On the number line, I marked the 0 at -4. And now I'm going to determine what happens in each section. All right, so I'm going to ask myself, okay, if I plug in a number that's smaller than -4 into that expression, what happens? I'll pick a number smaller than -4, do -5. -5 plus 4 is -1. So what that means is any number in that section will give a negative result. Pick a number bigger than -4. 2. Doesn't matter. Pick anything. 2 plus 4 is 6. That's a positive. That means any number in this section, continuing on forever to the right, will give me a positive result. That's what I'm trying to explain right here. Okay, any question on that? Now, I just did a number line for t plus 4. If this was a real problem, I would also do a number line for t minus 1, a separate one. And I'd have 2 number lines. And then the last step is to combine the 2 number lines together into one. Some people just jump to combining them right away. I think that gets a little confusing. If you can do that, go for it. But I'll do each one separate, and then I'll combine them together to answer the question. Okay, so a sign pattern is just a way of thinking about where a calculation is positive and where it's negative. That's all it is. And the reason we want to think about where things are positive and where things are negative is because every problem I give you is either going to ask where is something positive, greater than 0, or where is something negative, less than 0. That's why we're doing that. Now, the reason you've got to use the method I just showed you on this one is because of that number right there. If that -5 wasn't there, I could do this problem just like we did the ball off the ground problem. You could do it the same way. Just factor an x out. But I can't factor an x out of a 5. There's no x there to factor. All right. So we still have to factor it, but it's not as simple as just factoring an x out. We got to factor it like this. Let's figure out our first two terms. Sam, what can I multiply together here and here to give me 2x squared?
2x times x.
Perfect. 2x times x. Okay, the goal of these isn't to give you like the world's most challenging factoring problem. The factoring is going to be pretty straightforward. I want to see if you can do the number line. All right. So I'm not going to give you a number in front here like 24x squared. Because then 24, you got 2 times 12, 8 times 3, 60 times 4, you got a bunch of stuff. There's only one way you can get 2. 2 times 1. All right. What about my signs? I got a positive middle and a negative constant. Yep, Isaac?
Well, minus on the first one and plus on the second.
All right. So minus plus, it could be plus minus. We can check it after. And then to get 5, there's only one way you can get 5. 1 times 5. Let's check and see if it's right. 2x times x is 2x squared. I know that. -1 times 5 is -5. I know that. But the question is, do I get 9 in the middle? 2x times 5 is 10x. -1 times x, that's a minus x. 10 minus 1 gives me 9. So, yep, that's perfect. So now we've got our two linear factors. 2x minus 1 and x plus 5. Okay, what would you plug in for x to make that first set of parentheses come out to 0? Michael?
1/2.
1/2, yep. 2 times 1/2 is 1. Take away 1 is 0. So I'm just going to put a 1/2 right here. We'll figure out positive and negative in a second. Let's do the second one. What number would you plug in for x in the second parentheses? -5. Okay. These are two separate number lines. They're not to scale. They're totally separate right now. All right. So let's see what happens if we plug in a number smaller than 1/2. Okay. If you want to try one in your head, think like 0. If I plug in 0 into that calculation, what kind of answer do I get? I get a negative. So anything smaller than 1/2 is negative. If I plug in a number bigger than 1/2, like 3, 2 times 3 is 6, 6 minus 1 is 5, that's a positive. If you're wondering, is it always negative positive? Yes, unless you do something like that. Putting a negative in front of the x now reverses the sign of everything. So unless you factor it like that, which we never factor with negatives usually like that, that shouldn't be an issue. So plug in a number smaller than -5, like -10. -10 plus 5, that's a negative. Plug in a number bigger than -5, like 0. 0 plus 5, positive. Now we're going to combine those two into one number line. So on this one, we're going to mark both roots on the same number line. Doesn't have to be to scale, just put them in numerical order. -5, 1/2. This number line is going to tell us the final answer. All we have to do is check 3 sections, okay, and figure out are we negative or positive. So let's check the first section. That's numbers that are less than -5. Okay, so we have to check it in each one. So I'm going to go back up to my number line. If I look at my top number line, if I'm in the section that's less than -5 in the top number line, is that the negative or the positive section? Negative. Yeah, I didn't mark -5, but it would probably be around there. So less than -5 is a negative. Just write that down. And how about in the bottom one? Less than negative 5 is another negative. So if you're less than negative 5 in both, you'd have a negative times a negative, which would be what kind of number? That would be a positive. So now in the final answer, if you plug in a number less than negative 5, you're going to get a positive result. Well, that's part of what we want to know. We're looking for positive results. But we have to check the other two sections and see if they work. Okay, between negative 5 and a half. If we look at the top number line, negative 5 would be about here. A half is there. What section am I in there? Negative. Negative 5 is here. A half would be over there. What section am I in now? In the bottom one, negative 5 to a half. That would fall in the positive section. What's a negative times a positive? Negative. What always ends up happening in the final answer is the sections alternate. Positive, negative, or they could start negative, positive. But they always alternate like that. I would suggest checking the first two. And then if they come out different, you know you're good. If you check the first two and you get positive, you didn't do something right. Okay, they should always alternate. So this should be positive, but I'll check it this time just because it's our first one. So we're looking at numbers bigger than a half. Bigger than a half, that's positive. Bigger than a half, that's positive. Positive times positive is a positive. And that's why I put positive right there. All right. So now the answer is either going to be the positive sections or the negative sections. It just depends on what the question asked. This question is asking for the positive sections. Where are you greater than 0? So that would be here and here. So just write down what those sections are. X could be less than negative 5. So any number less than negative 5. Or x is greater than a half. Either way. Both sections work. If they ask you to write it as an interval, you can pick any number from negative infinity up to, not including, negative 5. Or, probably seen that before, but that's the symbol for or, when you write an interval. You can pick a number from a half as high as you want to go. That's how you solve a quadratic inequality. Any question on that one? All right, let's try this one. It's another quadratic. I made it a little easier this time. I've already factored it for you. So it's x plus 3, x minus 1. And we already did a positive, so why don't we flip it around and make it a negative. That doesn't change any of the work we do in the problem until we write the final answer. So let's just try this one as a negative. Okay, let me just kind of cheat and graph that real quick and make sure I gave you a problem that's doable, because anytime I change something, I don't want it to end up being a problem that's impossible. So x plus 3, x minus 1. Let's hit graph, and I'm just hoping that it goes negative somewhere, right around here. So that's fine. Okay, so this will work. All right, so let's make our number lines. What value would you plug into x plus 3 to make that 0? Negative 3. If you plug in numbers smaller than negative 3, you'll get negative results. Plug in numbers bigger than negative 3 right there, positive result. Okay. How about x minus 1? What value would make that 0? 1. Plug in numbers smaller than 1. You'll get negative answers. Plug in numbers bigger than 1. Positive answers. Right. Now we'll put it all together on the same number line. Okay. Put your roots, but make sure they're in numerical order. -3 and then 1. And let's check. We'll just check the first 2 sections. And if they alternate, then we know the next one will just alternate as well. All right, if we are less than -3 in the top number line, what kind of number would that be? Negative. What if we are less than -3 in the bottom number line? Negative. You just have to imagine where -3 would be, maybe right there. Negative times negative? Positive. So what should the next section be? Should be negative. If it is, then we're good. Between -3 and 1. So -3 is here. 1 would be to the right of it. What section are we in on the top number line? Positive. Between -3 and 1, that's in the positive section. How about in the bottom number line? Between -3 and 1. That's in the negative section. Positive times negative. Negative, the last section will be positive. Okay, so this time they want to know, where are you less than or equal to 0? Okay, so make sure we take into account the equal to. All right? There's only one section where you're less than or equal to 0. Right there. All right, so that's between -3 and +1. So we could write that as a conjunction we learned yesterday. Smaller number on the left, bigger number on the right. Anything between -3 and 1. Or if they asked you to do it as an interval, you can pick any number from -3, including it, up to 1, including it. Good. Any questions on that? All right. So if you can't factor, we'll try graphing it. Okay, that's something that's too complicated to factor. It's got this cubic here, that's going to be hard. So we'll just graph it, and we're just going to look where one color is above the other. So let's just type it in. We got x cubed minus 2x squared minus 5x plus 7. So I want to know where the graph in blue is above or equal to the graph in red. So where is the graph in blue above or equal to the graph in red? Let me get a better window. Yeah, that would kind of work, but I think this will look better. So, graph in blue, it's kind of this curve. Where is it above the graph in red? Since it goes off the screen, I'm going to go a little higher. Alright, so there's the graph in blue. There's the graph in red. Okay, so let's look at it. How many sections, if you look at that graph, does it look like the graph in blue is above the graph in red? Yeah, I see 2 sections. From here to here. So I'm going to find those 2 points. So that in that section, the graph in blue is above the one in red. And then from here on forever. Okay. Anywhere else, if you pick an x value in here, the graph in blue would be under. Okay, they specifically said above. So we'll do second calc intersect. Pick blue, red, do the guess. So I've got the 1 in the middle. So from something up to 0.76. So the answer is, I write it. Up to, and I can include 0.76 because, was there, I have that equal to. All right, so up to 0.76. Does anybody have, let me move my graph back. Does anybody have this one?
Yeah.
What's that one?
Negative 2.26.
Negative,
2.26.
okay. Just, I don't know if my tick marks go by ones, they must not, because negative 2 is over here, but they probably don't go by ones. So negative 2.26. So pick anything from negative 2.26 up to 0.76, or pick anything from here on. So does anyone have what that other point is? Yeah.
I'm just wondering what it. Can I see where you put in your calculator? Because I'm not getting what you have.
I can put that right over there. Okay. What's that last intersection point? About 3.5. Yeah, so my tick marks definitely don't go by ones. That's okay. What is it, 3.5? 0.7. So I'm going to say 3.51. So when you get a graph that's too complicated, or even if you get one you can make a sign chart for, you could always double check your answer on the calculator. Okay. But on the test, if it says to solve with a sign chart, and you just solve it graphing, and I don't see you made the number line, you wouldn't get any credit. So just make sure you understand how to do the sign chart, because that's what I'm more concerned about that than doing an intersect. Okay. Did you get that, Connor, now?
Yeah, I
Okay.
don't know what was going on.
Something weird. Okay, so that finishes up chapter 2. Okay, so for chapter 3, some of the things that we've done, okay, I've already mentioned a little bit, so it might be a little repeat at first, but we'll be getting into some things that you probably haven't seen before. Alright, so first I'm just going to try to describe what a polynomial is. It's kind of hard to explain in general, but the idea of a polynomial is it looks something like this. That's what polynomials look like. They have coefficients in front of the variable, like 8, 3, -2, whatever. They have letters. There's only one letter throughout the entire problem, just X or L or whatever the letter is. And usually we write it so the exponents start with the highest, and then they go down by 1. So 4, 3, 2, technically there's a 1 there. And then the last term is just a constant. There's no x with it at all. That's like my -4. Now the key that makes this a polynomial is that the exponents have to be non-negative integers. If I make this a decimal, nope, that's not a polynomial anymore. Exponents have to be non-negative integers. So that means any number from 1 and up. I can definitely put a decimal right here. That's fine. 8.1x to the 4th. That's good. You can put any number you want in front. But the exponents have to be non-negative integers. You also can't have something like this. Whenever you have a variable in the bottom of a fraction, that means that it really had a negative exponent originally. Okay? So no variables in the bottom of a fraction, which is kind of covered by saying this. Non-negative integers. And then the second part, if you want to translate that, it says that the number in front is a real number. So 8.13, whatever number you put in front, it can be anything you want. Positive, negative, fraction, or decimal. It's just the exponent. It has to be a non-negative integer. That is not a polynomial. Square root of x. No square roots in polynomials. So what's nice is there's no square roots, there's no fractions with variables in the bottom, so that means you can plug in any number you want. You'll never run into an error with a polynomial, with the domain. You can always plug in anything you want. So what we usually do is if you look at the highest term, okay, like in this one I skipped a couple. I don't have a cubed term, I don't have a fourth power term. That's fine. But if you look at the first term, and you look at that exponent, which is what n is the exponent, it tells you the degree of the polynomial. Now I say as long as the coefficient isn't 0, because if you do this is kind of cheap. That's not a degree 5 polynomial. You might as well just erase this. That doesn't even exist. So now that's really a degree 2. Right, so as long as they don't do something cheap and put a 0 in front, the highest exponent is your degree. Now, some have special names. The highest exponent is a 1. That's linear. That's something like that. If the highest exponent is a 2, that's quadratic. And if the highest exponent is a 3, that's cubic. Okay, beyond that, we would just say we have a polynomial that's degree 10, degree 15, degree 1,000, whatever it is. Okay, we don't really use too many special names beyond that. Okay. And this is what I told you earlier. The domain of a polynomial is all real numbers. You can take, looking at 2x plus 6, you can take any number you want and double it and add 6. There's no number you're not allowed to double. Let's look at this one. You have to cube a number, multiply it by 5, and then square the number, multiply it by 8. You can square any number you want, you can cube any number you want. So the domain is all real numbers. So if you get a question, what is the domain of this polynomial? You shouldn't even think about it. All real numbers. The range depends. I can't tell you the range. That's different in every problem. But at least the domain is the same. So cubic functions can look something like that. The idea is that if I were to put an x-axis in here, a cubic function can, doesn't have to, but it can cross the x-axis 3 times. The number of times it can cross is controlled by the highest exponent. That highest exponent is not a guarantee it crosses 3 times. It's an upper limit. Could cross 3 times. Another way to think of that highest exponent is if you subtract 1 from it, it tells you how many turns the graph can take. Again, could take, doesn't have to take. This one goes up, starts to make a turn, that's the first turn, comes down, makes a second turn. So that graph makes up to 2 turns. So how many turns could a 4th degree polynomial make? 3. Could make up to 3, which means it could cross the x-axis up to how many times? 4. Yep. So in general, that's what a 4th degree polynomial could look like. If you put an x-axis in there, it could cross 4 times. But maybe it only crosses 3. My x-axis was there, it would only cross 2. If it was there, it would just touch it once. And if it was there, it wouldn't cross it at all. Okay. Usually, the more complicated you make the polynomial, the more twists and turns it takes. If I get rid of some of these terms at the end, like let's just say you type this in, that's the simplest fourth degree polynomial you can have. It would actually look something like this. Kind of like a parabola, but a little flatter on the bottom. Okay. To get something that looks more like a W shape, you got to add in all these other terms. You got to make it, if it looks more complicated when it's written as an equation, it's probably going to look more complicated when you draw it. Okay, let's look at this one. It says to graph it and then find the domain and range. Well, it's a polynomial, so let's start with the domain. What's the domain? All real numbers. You can raise any number to the fourth power. You can cube any number. You can square any number. You're not square rooting. You're not dividing by letters. So it's all real numbers. To get the range, that's where the graphing calculator will help us out. So we've got x to the fourth plus 5x cubed plus 2x squared like this, 2x squared minus 8x plus 1. Okay, I'm going to do zoom 6, but it's probably going to go off the screen. It's probably going to have the W shape, yep, because you've got all the terms there. To me, it looks kind of complicated on paper. It's probably going to look complicated when I graph it. All right, I got to go a little lower. So let's try, I don't know, -20. So as you look at that graph, does it go down forever? No. It has a lowest point right there. Does it go up forever? It does. Yep, it does go up forever. You can zoom out and check it, but those two sides are just going to keep going up. Okay? A fourth degree polynomial can't turn more than 3 times. I can see all 3 turns on the screen, so it's never going to turn again. It can't turn off the screen somewhere. It's impossible. So it doesn't go down forever, which means it has a minimum. So we're going to find the minimum by doing second calc 3. Okay. Move your cursor over there. Pick a value to the left. Pick a value to the right. And do a guess. So the lowest y value that this ever hits is -11.95. And it'll go up forever from there. So my range is -11.95 and up. Never stops going up. Yep, Connor?
Can I see what you're trying to calculate again? 'Cause I don't know what's going on.
That was an X with that black box. Eventually, you're going to kind of learn a pattern of what these things look like. Anything that has an even exponent as the highest, the ends either always go up, like a parabola, or they always go down. One or the other. Okay? So we'll learn more about the patterns later. But for now, we can just use a calculator. Yep.
Can I show you what's going on? Because I don't know what's up on my calculator.
Keep it in right there. Let me take a look at it after.
Hey Connor, ours like look different.
No, it's going further down than it should be. That's what's going on here.
Just don't delete it. Just keep it in there for now, and I'll keep that there and I'll come look at it in probably like 5 minutes. Right, we'll be all done. All right. So 5th degree polynomials. I'm not going to get into that, but it's the same idea. 5th degree polynomials can cross 5 times. They can turn 4 times. So they could do this. Up, 1, 2, 3, 4 turns. So there's your 4 turns right here. Now, each one of those things I just circled those are called local maxes and mins. What that means, when you say that's a local min, you're not saying that it's the lowest value. You're just saying that in that area, it's lower than anything else. Okay? Just like that. A local maximum doesn't mean it's the highest value ever. It just means in that area, it's the highest value. And that's what I just said. So you could summarize these two basically in the same thing. If you just put local max / min, and then in the definition, it's a point on the graph that is higher or lower, depends on which one you're doing, than all other points around it. Okay, so you don't have to write it twice. I would just do it with the slash like I did. A local maximum or minimum is a point that is higher or lower than all other points around it over a certain interval. And that's exactly what I wrote for local minimum, so it's the same definition. Just put higher / lower. So what you might see for directions in a problem is find the local extrema. What that means is find the local maxes and mins. Okay? And we just did that in the last problem. Whatever it came out to, negative 11.95, that was a minimum. So you find it exactly the same way. So let's find the local minimum of that graph. So it's x cubed minus 4x. So in my head, cubed, I'm thinking, okay, cubed can turn 2 times. 1, 2. So it could look something like that. Roughly. Okay, let's see. So x cubed minus 4x. X cubed minus 4x. My window's a little different, but it's good. That'll work. Local minimum. Local minimum is right there. So they're asking me 2 things. What is the minimum? Where is the minimum? Okay, I'm going to show you how you answer that. So second calc, minimum. Pick a point to the left. Pick a point to the right. Do your guess. What is the minimum? Where is the minimum? Both answers are right there on the screen. You just have to know which one is which. So, what is the minimum? That's the y value. That's what the minimum is. It's the lowest y value it ever hits. So this is what the min is. The x value is where it is. That's the number that I would plug in. If I plug in 1.15 for x, I will get a value of negative 3.07. So the y value is what the actual minimum is. The x value is where the minimum is. So this has a minimum value of negative 3.07, and it occurs when x is 1.15. Okay? Just make sure you know which one is which. I'm not going to do the local maximum, but that would be right there, and you'd answer it the same way. Just do second calc maximum. Alright, so this is pretty straightforward, but just make sure people know what I mean by increasing and decreasing. If you look at that graph, where is the function increasing? From what letter to what letter? Yeah?
B to C.
From B to C. So from B to C. So the function is increasing. Where is it decreasing? Yeah.
A to B and C to D.
A to B and C to D. So if you look at it, look at what happens as you go from increasing to decreasing. Anywhere. You're increasing, all of a sudden you switch to decreasing. What do we call that point right there? We just went over that. That's a local maximum, yes. Anytime a graph goes from up to down, you get a local max. What about as a graph goes from down to up? Down to up, you get a local minimum. Yep. So you get a local minimum. Right. So if you can find local maxes and mins, if I go back to this problem, you could tell me where this function is increasing and where it's decreasing. I didn't find this one, but I think it comes out to negative 1.15. So if I find it, this function is increasing up to the red dot, and it's increasing from 1.15 forever. Where is it decreasing? Just in that little section right there. That's where it's decreasing. So when they ask you to find where a function is increasing and decreasing, you have to find the local maxes and mins. That's what I'm trying to explain right there. Okay, any questions? Okay, so some of it requires graphing calculator, but it's not too bad. All right, so the first part on page 116, that's the stuff we finished up from, we did a 2.5. And then page 149, that's the stuff from section 3.1 on polynomials. Page 149, I think almost every problem is a graphing calculator question, so there's not a ton of stuff to work out by hand. So as long as you get your graphing calculator, you should be okay. Just a reminder, I'll be after school tomorrow. So if there's any tests people need to make up that are within the 2 weeks, you can still make it up. Tomorrow's the last day to do it after school.